Okay, so let's start. So this is Crucial Python week 5, and today we're going to be talking about NumPy's outer functions. And these are going to be ways to do kind of all pairs computations efficiently, and I'll show you examples of why this matters. So just get started, bring in our PyLab setup, show our logo because that's important. So let's start with an example. So let's say we have two lists of numbers, call them A and B, and they can be of different lengths. And our goal is to find all pairs A sub I, B sub j, such that A sub I is within some distance R of B sub j. Right? So this is just a range search. It's not a difficult thing to do. You can just do it by kind of exhaustive search or a nested loop if you like. And that's very easy. So here's a function that just makes data of this form. So A is just going to be evenly spaced numbers, and B is going to be random numbers, and I'll sort them just to make it easier to print them. And here's a function that just finds points A, B that are within R of each other, and this is just a nested for loop. So you see for each AI and BJ, we add it to our list hits if the absolute difference is less than R, and then we return the array. Very simple. So let's just generate some test data and print it out to see what we're working with. So we have A starts at -2.5, goes up to 2.5, and B are just kind of random numbers. And we're going to set R to 0.25. And we run this find hits function, or find similar points. And we get 0, 0 matches, 2 and 3 matches. Right, so -0.5 matches to -0.32 because they're within a quarter of each other, and so on. So that's an example of the kind of all pairs computation we want to do, right? So all indices of A versus all indices of B, where do they match up? Slightly more involved example is interval intersection. So say we have two sets of intervals. So these are slices of the real number line. And we want to compute the size of the intersection between all pairs, right? So let's say S. So each interval goes from Si to Ti. And the intersection of two intervals, interval I and interval j, is just the, it's the minimum of the end minus the maximum of the beginning, and then threshold that at 0, right? This is an equivalent way to compute this. And here I'm just generating random interval data. So we just have random numbers, and then we add random numbers to get the endings of the intervals, and then we just return starts and ends. So to find the overlap between intervals, again, it's the same kind of nested for loop. So for each, we have one set of intervals that are indexed by start and end, so S and T, and these are of the same shape. And we're going to build a matrix that's all pairs of intervals, how much do they overlap? And this is just the nested loop that does that computation. So let's make some interval data and print it out. And these are in sorted order by start time. So the first column is the starts, second column is the ends. And now we can print a 5x5 matrix that shows how much each interval overlaps with all the others. And we get this matrix. So take my word for it, this is correct. So in both the examples above, we had these nested loops that are doing this computation. And that's correct, it'll work, but it can be slow. And the more loops you nest inside each other, the more work the Python interpreter has to do. But the actual operations themselves are very simple. And actually, NumPy provides kind of a secret ingredient that lets us accelerate this. And it's called outer, and it applies to any sort of universal function, or ufunc, as they're called in NumPy land. So just some examples of universal functions that implement this idea. So addition, subtraction, multiplication, division, comparisons like less than, greater than, or equality, bitwise operations, etc. The idea here is that you can give in two lists of numbers, and it'll build a matrix of all pairs comparisons applying say, addition, right? A sub I plus B sub j. You get a matrix that's the all pairs sum. So you don't have to write a for loop to do this. You just call sum.outer on your two lists, and it builds it for you. And this is nice because that's going to be implemented in C. It'll be fast, so it doesn't have all the Python interpreter overhead. So we give a link to some available U functions and show what they can do. But let's just go back to our previous examples and see how we can implement them with U funcs. So the first one, where we're doing the point range search, we have two lists, A and B, and a radius R. So we call np.subtract.outer with these two arrays. So A is a list, B is a list. We build the all pairs subtraction matrix, take the absolute value, and now we have that exact computation that we were doing before. But now this is much faster. And then we do the threshold at R. So anywhere the difference is less than R, we compute the argware of that function, which returns everywhere the matrix evaluates to true. And that gives us exactly the same kind of data out as we had before. So let's make some more point data. So here's what the old version does. Here's what the, right, I have to actually execute that. And here's the new version. And you can see they're equivalent. And now we can do a timing benchmark and see, did we buy anything by doing this? So timing the first one takes 187 microseconds per loop. New version, 31 microseconds per loop. OK. So that's like a 6 times speed up. But if we make a larger data set, so instead of doing 5 by 5, we're going to do 500 by 1,000. Benchmark the similar points. Now it takes 1.4 seconds to execute this find similar points function. And the fast version, 5.8 milliseconds per loop. So much faster. Do the same trick with the interval overlap. It's a little bit more involved because now we have to do a maximum outer for the starts of the intervals, a minimum outer for the end of the intervals. And now we have these two n by n matrices. We subtract the start from the end, threshold at 0, and that gives us our overlap matrix. So again, let's make some more data. This is the new version of the interval overlap, and it looks correct to me. So again, timing benchmarks. This is going to be a 5 by 5 computation, 85 microseconds, and the fast version, it's faster so it can do more of them. 18 microseconds, so again, pretty good speed up. Now if we go from 5 by 5 to 1,000 by 1,000, and run the benchmarks again, we should see a more substantial speed up. So the old version took 3 seconds to build the 1,000 by 1,000 matrix, and the new version takes 15 milliseconds. So pretty hefty speed up. And that's basically it. Of course, outers are much more powerful than what I'm showing here. It doesn't have to just be an n by n matrix, but I'm not going to talk about that today. One note is that this does build the all pairs matrix, and that might be more memory than you want to commit, especially if you don't care about the full matrix, if you only want to pull out subsets like we did with the hits. So there is a time versus memory trade-off for using outers versus using nested loops. But for the most part, it's usually worth it, in my experience, to do the all pairs matrix and rely on fast operations. And that's basically it.